Okay, good evening. Right, it is now 6:40. Okay, let's start our lecture. So before we go into today's content, we talk about this memory and cache as a computing lecture. Okay, before we go to it, just take a look at our midterm results. Okay, so our midterm is already released. Uh, Looks like a very flat distribution, right? So if you look at the CDF is a totally straight line. Okay, if it's a bell curve, the CDF will look kind of like S shape. This is the bell curve, but this is almost a straight line. It's almost a slight convex curve, right? If a convex curve, it indicates a slight trend towards the lower half. So we can see median 50 percentile is actually about here, which is not terribly good, right? Because 15%, if we take passing mark at 15%, it seems like 70% of the cohort has failed their midterm. Okay, so this 70%, if you are below this percentile, then you should work harder for your final exam. Okay, but granted this is a midterm, first time doing it. Okay, you do badly, never mind. Like I said, your final exam, you do better than your midterm, then we will not consider your midterm. Okay, we give you a chance to improve. Okay, let me take this mask, is very hot. Okay. Yeah, x-axis is the marks range. Okay, the bracket range. Okay. Right, so midterm is not as bad as a PE. So PE results we have finalized. I just finalized it. Okay, so I was in discussion with some of the tutors on the grading. So this is your PE results. Actually, PE right, over 10, but as you can see, most of you are like 4 to 5 marks, right? 3 to 4 or 5 marks. So not too bad lah. The 50 percentile is about here, right? This is about here. Okay, so it's still about half the class did fairly okay. So actually, not too bad. More than half the class passed, right? So if you are considering this is the passing mark, right? If you consider here the passing mark, okay, more than half the class. Oh, I think this I should color green because 5 over 10 is 5 over 10 actually can be passed. So I color wrongly. Wait, let me get color green for you. Okay, color green. Okay, color green. Okay, so don't look so scary. Right. Okay. So this is last year's how unhide the new hidden slides. Anyway, let me show you. This is last year's midterm. Unhide. So last year the midterm was over 40. Okay, so they had 1.5 hours. It was over 40. Okay, so they're about 50%. So similar. Okay, so their midterm 50% sort of failed the midterm. Okay, last semester. Right. This semester a little bit more, 70%. Okay, failed the midterm. Okay, but last semester we didn't have this final exam can cover over the midterm thing. Right, this semester we extended it to midterm. Right, so all's not lost. So even if you do very badly for midterm, it's not lost. Right, your final you can still do better than your midterm. Okay, same as your PE. Okay, your PE2, if you do better than your PE1, then we just take your PE2 results. If you do worse, then of course then we take average. Meaning if you are those who score full marks for PE1, right? Okay, then your PE2, whatever it is, your PE2, your PE1 will help you already. Right? You score full marks for PE1. Right? It means your PE1 will help you bring up your grades, okay, overall for your PE2. All right. I'm trying to get rid of this thing here. It's a hide. Okay. Okay, any questions on the PE? Okay. Okay, so today's topic, we go into memory. We talk a little bit about computing, we talk about memory, then we talk about what is cache thing. Okay, so this looks familiar, right? So we talk about this von Neumann architecture. Right? I think your midterm also we had you to put the label. Surprisingly, that question, still of you can get wrong, that labeling question. Okay, but maybe you didn't zoom in and see the clues that are on the board. Okay, but no matter. Right. This is von Neumann architecture where it uses a bus, okay, to transfer data. Actually, von Neumann architecture, his main insight, his main key is that your program and your data can reside on the same storage device. Right? To him, his insight is that programs are nothing more than just data, right, on a thing. So we can treat them the same way. That is his main insight, von Neumann. But people took the architecture and built it this way, where usually we have what you call a bus, okay, to move data from your RAM to registers, okay, and a bus to move from input device to RAM. Okay, so what you have is this bus. So just to recap the execution cycle, right? If you are using a load store architecture, or even if you're not using load store architecture, you always need to touch RAM. Okay, now registers are very fast. Okay, so before you need to, if you want to move your data from your RAM, you need to move them into your registers. Okay, so RAM is actually very slow. Okay, so before we talk about the slowness, we talk about this physical memory storage. Okay, so in memory, okay, you can view your entire memory as a continuous array of bytes, continuous bytes. Okay. Even though memory might be stored in a grid form or what, you can always enumerate them into a long sequence of numbers. For example, the address, our physical address in Singapore, right? Every one of us have a postal code, right? Even if you live in an apartment, HDB block, the whole block is one postal code, right? So of course, some divided into unit, but that one postal code identifies your block. And those who live in those private estate, right? One unit, one lot has one postal code. So even though your address is 2D, right? This is a very ugly drawing of Singapore. Okay, Singapore looks like something like that. Singapore looks something like that. Even though this is 2D, right? The estate, but everyone is given a unique postal code, right? So we have a 6-digit postal code. But I can arrange yours sequentially, right? From 0000 all the way to 99999. But of course, there are some missing gaps. We don't have a continuous sequence. Okay, so it's possible for us to enumerate, right? Serialize your address this way. Same as computer memory. Okay, so it doesn't matter how the physical address of memory is stored. Okay, we can always serialize them by a sequential address. Okay, so we can view memory as a unique index. Okay, so this is what we call a physical address. Okay, even though physically it's not actual address, so it's just like your postal code is a physical address, right? It identifies your location, right? But oftentimes the numbers don't give you much hint on the location, right? It's not in any pattern. Okay, so this is just a recap, okay, of what happens with variables and pointers. All right, so when you have a normal variable, when you say integer x, okay, what a compiler do is that the compiler will allocate memory. Okay, when a compiler compiles your code, okay, when it compiles into program machine code don't have variables one. Okay, these variables are just placeholders that we humans use, okay, for us to be able to manipulate the memory state much easier. Compiler will say, okay, you are using integer x, I will dedicate 4 bytes. So 4 bytes of memory here. Okay, maybe these are 2 bytes, this kind of memory. Okay, this will be referred to x. So in the machine language, this x will be replaced by 1024, I mean, whatever the current address is there. Okay, so that is what a variable is. A variable is just a mapping, okay, to a particular segment of memory. Okay, so how a pointer? When you do pointer, yeah, a pointer is also some segment of memory, right? So for example here. Okay, so a pointer also needs to contain data. But like we said before, the value of a pointer is actually an address. So in this case, if you say pointer is the address of x, so down here, if x address is 1024, so the pointer inside will contain 1024. All right. So if you say star pointer equal 123, it will come here 1024, go to 1024, and here put 123. Okay, so this one we have gone through before. Okay, so now arrays is a little bit tricky. We have talked about arrays a couple weeks back. Okay, so an array name is like a constant pointer. Okay, so we did say before, array decays down to pointer sometimes, right? So when you do something like this, when you tell the compiler integer ai is an array, an integer array of 3 values, what it does is it will create ia, okay, like this. Okay, so it might not, if you do this, okay, it does not actually create a pointer yet. Okay, ia is straight away into here. Okay, I think there's some alignment issue. So ia is actually this particular location. Now I say I have a pointer ptr. So ptr is this. Okay, there's an animation. Maybe the alignment looks a bit off. Okay, ptr is this. Okay, let's say ptr is this. ptr equals to ia. Now the interesting thing is that ia refers to this thing, but as it being an array, we refer it to as 1026. It is as if ia is like a pointer, as if. It might not be, but again, it depends on compiler. Like a compiler might just decide to compile ia as a pointer, okay, in your code. So it could well be that this is what happening. But the interesting thing is that if you ask for address of ia, they will give you this. Okay, but you do pointer equal to ia, that means pointer points to ia. So pointer is 1026. All right. If you do ia equal pointer, now what happens here? ia equals to the pointer. It refers to the same thing. Okay. This might not be valid. Okay, again, depends on compiler. Later we go and try. Now you say pointer 2 equals to 9. What happens is that you will follow the pointer, then jump to 1, 2, and then this will become 9. Okay, so a pointer can work as array. They are sort of like interchangeable. Yeah, I know it's very confusing. Okay, but there will be people who use pointers like arrays. Anyway, in our case, if you just treat arrays as arrays, then it is more straightforward. Okay, don't try to treat pointers as array. It makes this a little bit more confusing. Okay, but this example just shows that pointer equals to address of ia1. So ia1, ia is this, ia1 is here, right? And this 0, this is 1 index. So pointer equal this address, pointer become 1027. And then you set this pointer 1 equal 11. You set this, you go to 1027, jump down 1, and this will be 11. Okay. So interesting thing is this. Let's fire up Visual Studio Code. Okay, and see this thing about array. I'm not sure whether I can't remember whether I showed you all before or not. Okay. Anyway, let's create a new file. Right. Let's save this as a lecture8.cpp. Okay. So int main. Let's use a cout. Include IO string, right? Using namespace. Okay. Integer array I, right? IA, right? IA 3 equal 137. Okay, let's do this. Right. Then I say integer pointer okay, equals to IA. Right. So equals to IA. Let me see out lah. See out. Then we see out. Okay. See out. What's the address of IA? Address of pointer. Let's see whether we can see out. So I see out IA. Okay, we run this and we see, see how it goes. Okay, is there we're chatting here. Okay, the reference point. So this what I'm doing here is I'm sorry, should not be reference of yeah, create a pointer. Okay, maybe this one is a bit confusing. So I say pointer equals to IA. Okay, let's run and see. So IA and pointers are different. You can see IA is 40, pointer is 38. All right. So I think IA is yeah. So pointer is 38, address of IA is 40. Is here. Okay. Let's count. Let's see out the contents of pointer. Okay. If we see out the contents of pointer, how about contents of IA? Just like that, without the n %. Okay. Let's see what we get. All right. Notice IA is the same, but pointer is different. Okay. So what does this mean? What this means is that we have this IA here. We have IA. IA is okay. This one is E30. E30. I just use the last 3 digits. Okay. Pointer is somewhere here. 28 is actually above 30, right? So here's E28. Okay, so this is pointer, right? The content of pointer is E30. So let's take a look at what I'm doing, right? Address of pointer, very correctly is here, right? E28. And content of pointer, what is pointer? Inside the pointer is E30. Okay, E30 here, which is this. So this is a pointer to this. Now IA is very odd. The address of IA is also E30. The content of IA is also E30. That's because IA is an array. So this is where the confusion comes in. Sometimes it's a pointer, sometimes it's not. Okay, so this is an array. So inside here you have 1, 3, and 7. All right. So to add to the confusion, if you try to take a look at, let's do some modification. We do pointer 2 equals to 9. Okay. Then we see out pointer 2 and we see out IA2. Okay, once you run this, you notice, okay, both are 9 here. Basically, pointer, by doing this, pointer 2, what happens is pointer comes here, this is 0 index, 0, 1, 2, so equals to 2, it changes this to 9. Right, so you see IA has changed as well. So basically, these are 2 pointers that point to the same array. Okay, so this is what happens with a pointer. It's like passing by pointers, right? You can 2 pointer point to something else and you modify it. Okay, the example showed something more interesting. So suppose later on, I said pointer equals to IA1, address of IA1. Okay. Then I do pointer 1 equals to 11. Okay, then we print again. Okay, now what is this doing? Right, so let's take a look here. IA2 becomes 11. So what's happening here? So address of IA is this box over here, right? Which is address is E30, right? Address of IA is E30, E30. So naturally, address of IA1 is E31, E31. Okay, I assume it's E31. Let's go and print it. Okay. the out address of IA1. This address of IA1. Okay, we want to see. Address IA1 is where is it? E34. Okay, because 4 bytes, right? 4 bytes for integer. Okay, so this one is 4 bytes for integer. So this will be E34. Okay, so each integer is 4 bytes, right? So jump E34. So by this is E34, we are assigning into pointer, right? So pointer now inside becomes E34, which means it's no longer pointing to this array, is pointing to this. Okay, so when we do a pointer 1 here, what happens is it now jumps by 1. Change this to 11. Okay, that's why our IA2 also end up changing. So this is how pointers jump back and forth, Technically, I can ask pointer to jump 100. So I can always say pointer 100 equals to 11. Okay, nothing will stop me. Okay, nothing will stop me. I can easily do this. Okay, so this works well. Even though pointer 100 is, I don't know where is it. Somewhere here. We might touch other part of memory, might touch other functions. Okay, so I don't know, but it's allowed in C. Okay, so basically, end of day, a pointer plus an array basically just means from that point you're looking at, jump how many steps. Okay, that's what this square thing means for pointer. So in C, pointer and arrays, they are oftentimes used interchangeably. Okay, people treat them interchangeably because all they do is allow you to access, move up and down, arbitrarily move up and down the memory stack given to you. So as you can see, I can just anyhow go up and down the memory stack and change variables wherever I want. Okay, there is no control. We've always said in C, there's no control, no one watching over what you are doing. Okay, so you're allowed to mess up with things. Okay, I think last week we watched the video, right? How you can write read 4,000 bytes of memory, right? In the hack, okay, in the exploit. So this is basically what happens, okay, in C. All right. Back to our lecture. Okay. So now comes the interesting part. Okay. So in the executable, your source code, this is like your standard source code. After compiling, okay, you will compile into some executable portions, which is a program part. And some parts of the program is the data part. Because like von Neumann says, right, code and data can be stored in the same place. So when your program is compiled, okay, data like this, I equals 0 and all that will be found inside some data late part in your program. Okay, so if you take a look at this, what happens with the executable? So this will be like your executable code. Down here, 0 is quite universal. Maybe you have some hard-coded numbers inside there, like maybe 1024 or something. Some numbers or constant in your program. Okay? Or it could be some constant string like hello, please log in, all this kind of constant string. Okay? All this will also be found in your program. Okay, so your program don't just contain instructions, it contains all this kind of interesting data. Okay, I mean, of course, this data can be part of the instructions or can be also part of the data that your program has. Okay, so after compiling, your operating system basically, what your operating system does is it sets aside some kind of memory for you. Okay, basically it says, okay, your program wants to run, I give you a chunk of memory. Okay, you do whatever you want in the memory. So your program will load. Okay, your operating system will load your code into the memory. Then after your code, somewhere here, you will say you can use it as your free memory to do your computation, okay, to execute your program. Okay, so you have some memory space given to you, you have some code, you have some data here. So as you run, obviously this data is basically for global variables. But how about local variables? That's what we say global variables not very good to use. How about local variables? Your parameters that you create. Okay? So basically, I mean, this is just scoping, right? Which I talked about previously before. So here have X, here have X, here have X. Okay, so scoping. Now what happens is that we have this different stack memory. Okay, I think we have been quite familiar. We've always been drawing for you, right? Every time you call a function, a new stack memory appear. You use ctutor or use Cake, we also want to show you the stack of memory. Okay? So what happens is this. As your function gets called, the stack memory gets stacked on top one after the other, like this. So this is main, then you go to F, then you go to G, so on and so forth, right? It goes up. Okay, it's like stack one on top of the other. Okay, each and all that. Okay, so once you're done, okay, the stack will erase. Okay, so in this case, okay, so every time you enter a function, a new stack frame is created. Every time you exit, a stack frame is destroyed. Okay, so that's why in scoping we can use shadow variables and all that, right? So basically, they occupy different portions in memory, in different stack frames. Okay, shadow variables, they create another it's a mini stack lah. Okay, so to speak, it's not really the full stack. Okay, but again, there's a bit more of details. So when you pass by value, like this, what happens is that we already mentioned, right? The value here will be copied into the value here, right? That's passing by value. If you pass by address or pointer, this thing will be a pointer to this thing. Okay, you pass a reference. Reference also works as well like a pointer. Okay, so pass by reference looks like pointer, but the interesting thing is if you ask for the address of A and B, if you ask for the address, it will be the same address as I and J. So during compile time, no pointer actually is created. Okay, what happens is that the variables is like mapped into the same memory location. So you can go and test it out. Inside your path of reference, you go and print what's the address of A and B. Okay, it will be the same as the address of I and J. Okay, because it is here. Okay, which is how it happens in memory. Now, so the memory space is here, your stack direction goes here. So it turns out, if you are able to reverse engineer, okay, reverse engineer a piece of program, and you find some kind of exploit, you see, you're actually able to go using pointer, right, using memory reference, go all the way back to here and change something. Maybe you can. It might be possible. So in this case, you have overwritten, compile, basically the program. Okay, you overwrite the execution of the program. Or you could do something. So maybe, okay, this one your operating system might be able to block. Okay, maybe your operating system say, okay, this part is protected memory. Okay, your program cannot touch. But it might be able to get some kind of function for the program to change the execution to here, then put some instructions here, then execute as those instructions. So all these kind of jumps and all these are all these little exploits, okay, that can be done in at the machine level. Okay, so that is how memory. Of course, the memory space is limited, it's finite. It's possible to go all the way until you hit the maximum. Okay, so you cannot reach, I mean, it's not infinite memory. So your program can actually run out of memory. Okay, so talk about memory hardware. Okay, so in memory, there are two types of memory. When people talk about memory, normally they refer to what we call the volatile memory. What's volatile? Volatile means easy to ignite, easy to explode, right? You say, wow, this person's so volatile, right? And a small thing only he trigger. Okay, so volatile basically is memory storage that requires power to retain. Okay, so once you turn off the power, you off your PC, your document is gone, right? So if you didn't save a document, it's gone because this document is actually in the volatile memory. Okay? So normally this volatile memory is called the RAM. So you ask you, well, your phone, how much memory, how much RAM your phone have? When they ask you about memory, normally they refer to RAM. It's not the same as storage Although these days people get confused between the two, right? Say, well, your phone got 16 gig memory. Actually, it's not memory, right? That's the 256 gig memory. Actually, they're referring to the storage space. So it's a bit different. Okay. But yes, in a way, they are also called memory. It's a non-volatile memory. Basically, storage that can retain information even if there's no power. Okay. For example, hard disk. Hard disk is made of magnetic tape. Okay, magnetic disk lah. Disk. So basically, they have this little magnet. Okay, so they rotate the orientation. Okay, north south, north south, north south. Okay, so we can actually use the magnet and control this little magnetic iron particles inside. See whether it's north or south, north or south. Then when we read, we can see this magnet is north, this magnet is south. So this is your ones and zeros. Okay, so we can do that very finely in magnetic disk. Okay, read-only memory is in the and nowadays, of course, SSD. SSD is not magnetic. Okay, we'll see how SSD work. Okay, so what's the memory technologies in the 1950s? So long ago, in 1948, right, we use a delay line memory tube. Okay, so these are some like vacuum tube. So it turns out like using vacuum and heat, you can actually store information for a little while. Right, it's like when you on a light bulb, it turns bright, right? When you off it, it takes a while for a light bulb to dim, right? Okay? So it has this little bit of a lasting effect inside. Okay, so vacuum tubes have a bit. So what you do is you have a tube. Okay, as it is dimming, you go and use the data to power a tube. Then you go and power it yourself again. This is basically what this volatile memory do. Right? In this case, okay, 1952. IBM has a magnetic core memory. Now this memory is ROM. It is a read-only memory, cannot be changed. What you actually have here is you have this iron ring. Okay, then you have this cable that goes in. It wraps around the iron ring, right? Then I think it wraps in one pattern. This is a 1. If it wraps around in some other orientation, okay, I don't know what orientation, it's a 0. Okay, so it's manually wrapped around. Because as electric current flow through, okay, it generates some kind of magnetic field, right? You all know when magnetic flow through like a transformer, it generates some magnetic field. So depending on how we wrap, the magnetic field will generate, we can be interpreted as 0 and 1. So all this memory are typically hand wound. So for example, the memory that controls the computer that was used to send the astronaut to the moon. Okay, it's all hand wound. You can go and Google. There's this team of ladies taking this called wine. This is a 1 bit. Wine is 2 bit, right? So they do it, right? So this is a 16 kilobytes. So if each of this is 1 bit, then or 1 byte, then you can see 16,000 of them. Okay, so they slowly wine all this. Okay, so last time these computers take a big, okay, this thing is one big case, only 16 kilobyte, you know. Today, one small little chip, 1 gigabyte already. Okay, so this was in the early days, right? Until now, we have this invention called a transformer. A transistor. A transistor that make everything so miniaturized. Okay. So in memory, this is how your normal DRAM works, dynamic RAM. Okay, dynamic RAM works. So how it works is that it's actually very simple. What we have is a storage capacitor, and then we have a read-write transistor. Okay, so the thing is, the capacitor is like an electronic battery. We can charge the capacitor up, then when you let go, it will discharge. Right? It's a little bit like the candle that I said, right? You put some heat in the light bulb, then when you let go, after a while, the light bulb cool off, right? So capacitor is the same. You build up some charge on one plate, okay? Then when you release the charge will slowly, you know, it will slowly trickle away. Okay. Now what you do is that before this charge fully trickle away, you go and recharge back again. Okay, so it's a bit like you have a bucket of water, right? There is leaky with a hole. You can fill water in a bucket, right? Then when you let go, the water will slowly drain out of the hole, correct? But before the water finish drain, you can look in again and see, oh, there's half filled. I'm going to top up. Okay, so you periodically have to refresh. So yes, for dynamic RAM, you must refresh every 64 milliseconds. Okay, or each cell, every single cell, you must refresh every microsecond or something. Okay, so basically, you must do a refresh. Okay. So the downside of dynamic RAM Okay, the advantage is very cheap because only one transistor, one capacitor, right? Just like this, wired together. Okay, but it's very slow. Okay, to read is very slow. So normally what they do is they put a whole bunch of this together as a cell. So you see you have 16 cells, so it's 16 bits here. Okay, so when you read, you can read access row by row by row, okay, using this selector. Okay, so they usually put it in a block like this. So the problem with this DRAM is it's very slow to access, okay, to read, because when you read, you need to wait for the capacitor to discharge, right, to figure out whether it is contain a byte or not. But usually purely refreshed. That means while it's refreshing, so imagine all these are like your cups of water, right? While you are refreshing, okay, so maybe you have a tap here. Okay, this is where the thing drains. So while you want to read, you just take a look like which container have water dripping out, right? You observe, then you know, oh, this is 1, this is 0, this is 1, this is 0. So when you read, you do that. But when you're refreshing, you must go through every one of them and look right and top up. So during the refresh, your memory is blocked. Okay, so you cannot access the memory while you're refreshing, doing one refresh. This is dynamic RAM. But it's very cheap. Okay, so dynamic RAM is what they use in your current RAM, your SDRAM. Okay, so SDRAM stands for double data rate synchronous dynamic RAM. Okay, so it's still dynamic RAM. Okay, it's very cheap. I mean, you might think compared to hard disk, it's more expensive lah, but technically it's still quite cheap. Okay, so if you look at the data rate, the prefetch is here. So if you buy any RAM, there's some statistics here, right? So what they say is there's a prefetch rate, blah, blah, blah. Okay, so these days, as you can see, the data rate climbed very high. Okay, so internal rate is 133,200. Okay, the transfer rate is much higher. So the voltage drops much smaller. Okay, so what they call this double data rate, okay, because this called clock cycle, right? Basically it's a timing, timing. Right? So you have this pattern of timing. Is you read, go and refresh, then do something else. So double data rate means you can, on the positive edge and the negative edge, you can go and examine the value of the RAM. Okay, so that's what double data rate, some kind of technology. Okay, so DDR RAM, yes, our speed and density have been improving. Okay, we are always improving from DDR, DDR2, DDR3. Last time it was not called DDR. Last time it was called SDRAM only. Or DRAM, then SDRAM, then 2002 you have DDR RAM. We've always been improving. Since we start at DDR4, nowadays we still using DDR4. Okay. But there's a problem, okay? Because even though RAM keep improving, but your RAM improve almost like a linear rate. Okay, your CPU almost sorry, it's not really like a linear rate lah. It's still exponential, but your CPU increases much faster rate, right? So nowadays your processor clocks at 1 nanosecond per clock cycle. If your DRAM needs 50 nanoseconds to access, it means you want to get one, read one byte from memory, you must wait 50 clock cycles. Means you can do 50 computation. Okay, that is the best effect. So this is basically what you call a memory warp. There's this delay, the gap between this. Okay, so what happens is we use registers, right? We all know we use registers. Now, register is what we call static RAM. Okay, now static RAM is done this way. Basically, you use 6 transistors, okay, each memory cell. So here, 2, 3, 4, 5, 6, 6 transistors. And it's very expensive, but you have six times more transistors. 6 times more expensive. And because it's bigger, you also cannot squeeze as much, okay, into the same space. Right. So the nice thing about this static RAM is that you don't need to refresh. In a way, you put data here, you can see there's the transistor here. In a way, it self-refreshes. You know, in a way, as long as there's a current, okay, the thing will self-refresh. So there's no need for refreshing, and access is very fast. You see, 0.5 nanoseconds to 5 nanoseconds is almost as fast as CPU already. Okay, so this is very expensive. Okay, to do so. So that's why we have these registers, which is very fast. They use static RAM. We have your RAM memory, main memory. okay, which is your SDRAM slightly slower. Then we have even slower still, hard disk. Okay, hard disk, as you know, is used to store huge amount of files, all the way up to terabytes. Nowadays, one hard disk you can go 5 terabytes. Okay, it's also a bit very cheap in compared to SDRAM. Okay, so how it works is that I said it has all this magnetic disk. So the head is here. This will spin. So it's like an old vinyl record lah. You know, it's spin. Vinyl reads groove. Okay, inside the vinyl. This one, the head reads the magnetic differences, okay, inside the disk. Okay, so basically, normally you stack many platters together, one on top of the other, and you read the top, you read the bottom. Okay, double-sided. Okay. Again, this is mechanical. So there's this spinning action, there's this head moving back and forth. So of course, with all mechanical movement, it's slow, right? Your head has some mass one. As you swing the head back and forth, you cannot stop instantly and go back, right? There's some kind of mass, inertia involved and all that. And again, with mechanism, there's always wear and tear. Okay, but again, this is a cheaper technology. Right? There's an even slower technology called magnetic drive, magnetic tape lah, which is basically like a cassette tape like that. Okay, instead of having this platter, we have it on the cassette tape. Rewind back and forth one. That one people use for backup. Because backup, most likely you write once, you forget, you don't want to access anymore. It's only when you need to go and retrieve your backup again, then you normally want to go through everything again. So magnetic is very dense. You imagine your small little tape, it can easily hold hundreds of terabytes inside one magnetic tape. Okay? Okay? Right. Someone asked why StudyMax got no refresh, because it has more transistors, right? So it uses 6 transistors. So the transistors, in a way, they will refresh themselves compared to SDRAM. SDRAM only one capacitor, one transistor. So that's the design of the components. Okay. Of course, the trade-off is cost, right? Use more transistors, cost more. Okay. So yes, we can easily build static RAM as large as SDRAM, but of course the cost will be quite high. Okay. So it's a more of an economical sense to it. Okay. Flash memory. So nowadays, your SSD, you use this thing called flash memory, right? So they have no magnetic component, so it's not mechanical at all. Okay. So what they do is very interesting. They use something like a transistor. Okay. So you know this is like a transistor, but they have some way of trapping electrons between the gate. Okay. So somehow you have some silicone substrate, then electrons get stuck in between. You remove electrons there and you remove power, the electrons get stuck inside, suspended inside this semiconductor thing. Okay? So that's how flash memory works. Then later on, when you check, you read the charge, see how much charge is there inside. Okay? So SSD is actually quite fast, not too bad. The high-end SSD, okay, latency is almost comparable to your SDRAM, okay, 15 microseconds. Sorry, wrong. It's microseconds, okay, not the nanoseconds. Okay, so it is much faster than your hard disk. Hard disk latency is milliseconds, right? SSD is microseconds. SDRAM is nanoseconds. Okay, SRAM is single-digit nanoseconds. Okay, so it is much. I mean, it's much faster than the hard disk, but still not as fast as your SRAM. Okay. The thing about SSD, there's this other limiting factor, is that each component has only a limited amount of writes. Okay. In a sense, it's to do with this trapping electrons between the gates. Okay. So after a while, there'll be some degradation, even though it's not mechanical. Okay. You move electrons in and out, in and out. Okay. When you come to this state, you are talking about in terms of quantum mechanics already. The electrons jumping here and there. So quantum mechanics actually play a big role in development of all these things. Okay, so due to physics, okay, after a while, this cell cannot hold electrons anymore. Okay, due to some physics reason. So SSD have a limited number of writes into a cell. So you buy your SSD drive. Okay, that's why people tell you don't go and use it as a scratch disk or whatever. Okay, basically because your SSD have a limited number of writes. Okay. Your SSD will have some kind of a smart driver. You'll try to distribute, okay, the writes across all the different cells so that your drive will wear down evenly. Okay. But the read, there's the unlimited read, but limited rewrites. Okay. Okay. Now talk about this differences in types of memory. So we see here, we have registers, we have RAM. This input output device, basically your secondary storage. Okay, so when people talk about storage or main memory, they will refer to main memory as your DRAM. Okay, so if you look here, in your CPU you have registers. Now these registers are very fast. They don't even might not even be done using SRAM. They are part of the fabric of the CPU, inside the CPU. Okay. Then sitting outside the registers, normally what you have here is some amount of cache. They call it cache. Later we'll talk about this cache. This cache is usually SRAM. So the cost of SRAM recent years is $400 per gigabyte. So we don't have a lot of SRAM lying around. Normally we only have megabytes of SRAM. All right. Okay. So then we go talk to DRAM. DRAM is much cheaper, $8 per gigabyte. Could be even much cheaper now. You can buy a stick of 8 gigabyte RAM for $15+, like kind of a thing. Okay. Then hard disk. Hard disk is super cheap now. You can buy 3 terabyte, 4 terabyte hard disk for $100+ only. Okay, SSD also. SSD have hit 1 gigabyte SSD. I mean, you can buy it now. Now, the ideal case is we want super high capacity, but we want to have very low latency and we want it to be very cheap, right? This is what we want, the best of everything. But unfortunately, in real life, we cannot have this kind of situation, right? It's all trade-off, right? In life, everything is a trade-off. Okay, you want capacity, then you pay for it in later. You want capacity, then you pay for it either in cost or latency, right? If you want big and cheap, then you become slow. Okay, so this are 3 factors trade-off. Okay, so now this best of both worlds, we cannot have that. Okay? So the key idea here, what do? We use a hierarchy of memory technologies. Okay, so we use a whole range of all these different memory. Okay, so what we do is we put fast memory near the CPU. Because CPU works very fast, right? So you put very fast memory near the CPU, but it's very expensive. So we use a small amount only. Registers, I think most CPU inside only have 10-20 registers only. Okay. Your SRAM, your cache, probably 256 megabytes kind of thing. Okay. Large or small memory, so you go to your SDRAM, your DRAM. Okay, normally you 8 gigabytes of RAM in your phone have 8 gigabytes kind of thing. Then you go to your SSD or your storage, SD card or storage, permanent storage device. All right. So this is the best of both worlds, right? So very fast, but very expensive. As you go further and further away from the CPU, so CPU is here. Here is like tape drive and storage. Okay, you are like miles and miles away from CPU already. Okay, you go very slow. Okay, so we can talk about this later. Let me see where we can start. Okay, we start by cache. So let's talk about this last part here. All right. So this is what we have. Okay. Now the question is this. When you write your program and you compile your program, right, or basically any program, it will all become data file, and we store in our secondary storage, right? So say SSD or your hard disk. All right. So when you want to run your program, we all know SSD is very slow. We cannot afford to run your program by reading one line of reading one instruction from SSD execute. Reading one instruction from SSD execute cannot, right? Because SSD, the fastest is what? 50 microseconds, right? CPU runs at what? 0.5 nanoseconds, right? This is like 1,000 times slower. 1,000, right? No, 1 million times. Is it? Micro, then 1,000 times. 1,000 times slower. But if you are using hard disk, right? HDD, right? Hard disk is like 50 milliseconds. Okay, this one is 1 billion times slower. right? So we cannot afford to just run your programs directly off your secondary storage, which is why your operating system takes your program, loads it into RAM. Right? It will read everything into RAM. That's why big programs, you realize why when you open a big program like Microsoft Word or what, it takes so long to load, right? Loading thing come out. Basically, operating is doing this. Microsoft Word has tons of instructions, super complex, right? As compared to a small little, maybe your program like WinZip or something, it's a small little utility program, very, very small, very fast. But Microsoft Word seems to be lots of features, lots of things, right? So they'll have to load everything into RAM. Now, this Chrome also does the same thing. This Chrome is this big giant bloat thing. Technically, browsers should not be too big, but now Chrome, a lot of features in there. It has this whole HTML5, JavaScript engine in there. So also takes a long time to load into main memory. Same as your phone app. Okay, your phone app also says same things. Sometimes you click your app, takes so long to load. Basically, it's just loading all the data from your phone. Okay, your phone internal memory is like a SSD. Okay, it's like SD card. It's like I know some phone nowadays no more SD card slot. Okay, so the SD card is sort of like burned into the circuit. So same thing. It's very slow. Okay, so it takes a while to load into your phone memory, your phone RAM. Then your program can start. Okay. So the thing is, when you want to load stuff, RAM to register. RAM operates at 50 nanoseconds, right? It is still 10 to 100 times, 50 to 500, okay, thereabout. Okay, so it's about 10 to 100 times still slower than your processor. It's still slower. So even if you're reading one instruction at a time from RAM, you are delaying your processor. Your processor, remember the memory war? The processor can go quite fast. 10 to 50 times faster. Okay? So in order to make slow memory appear faster, what happens is that we make use of this thing called a cache. So we use SRAM to build this cache. So data will come into the cache first, then from the cache, go into the register. Okay. Now, this cache thing is very interesting because it's supposed to be transparent to the programmer. As programmer, especially C programmers, C++ programmers, what is not transparent to us is RAM, right? RAM is exposed to us. Okay, when you deal with arrays, you deal with pointers, you are directly manipulating RAM, the memory allocated to you. Okay, like just now I show you, you can do a call pointer and access pointer 100, means you're touching somewhere in RAM. So this whole RAM is given to you. The operating system will give you this chunk of memory. Of course, you cannot go and write into other programs' memory, and the operating system will block that. Okay, so but this RAM is basically what you see. Now this cache is transparent. Okay, so to a programmer, you actually don't really know or don't really bother of this interesting cache that sits between. This cache that tries to make things faster for your program. Okay, so this is what we'll be talking about this week or later on after the break. Okay. The next part here, how to make small memory appear bigger. Okay, so here's the thing. Okay, this one we'll talk about 2 weeks later when we talk about operating system. Okay, so but here I motivate, right, because there are 2 aspects. So first one is main memory is very slow, or the main memory is still very slow. To make it faster, we have this intermediate cache. Now, main memory is also not very big, right? If you think about it, most computers these days 8 GB RAM. Your laptop 8 GB RAM stick. You go and press the Control Alt Delete and you do Task Manager, like me. I do Task Manager. Okay, so let's take a look at this system. So, is that information? Let's see what's my information. Press System Break or Windows Break. Right? Yeah, no, I'm looking for the total RAM that we have. This doesn't say the total RAM. Is it where does it say? Oh, okay. So we have 15.9 gigabytes of RAM. Well, this computer not too bad. 15.9 gigabytes. Okay. But in total, we're only using, actually we don't need, we're using 40%. Not too bad, not too bad. Okay. So we are using 6.3 compressed, we have available 9.4 left. Okay, so this computer is not too bad. Okay, we have not overrun this. This one is very interesting. So CPU, you see, you have this cache, okay, which are your SRAM. So you see this L1, L2, L3. Oh, it's not even megabyte, sorry, it's kilobyte. Okay, the biggest one is 8 megabyte. Right? Because it's very expensive. 1 gigabyte is $400. If you have 1 gigabyte, your CPU will cost thousands and thousands of dollars. It already costs so expensive, your CPU. Put more cache in there is even worse. Okay, so how do I get this memory to blow up? Let me think about it. Is there any way to blow memory up? Let me Google it. Okay, how to stress test PC memory. Okay, memory. Okay, mem test. RAM test. I with Windows 10. Actually, I don't know whether I can run it or not. 3D Mark. 3D Mark test your RAM and GPU kind of thing. Maybe we'll try 3D Mark. Basically, Prime 95 calculates prime numbers. Okay, we always test memory. We can always try. Oops, this is not useful. Prime 95 here. Okay. Prime 95. Operating system, Windows 64-bit. Hey, why I can't download securely? This is so silly. It says you try to install malware. How come? Why you think it's malware? Hey, this can't. Maybe you need to use Edge browser. Edge not so secure maybe. Prime 95. Prime 95 download. Okay, save. Okay, so Edge is not so secure. Edge, let me download it. Okay, I open Prime 95. Let's click Prime 95. Extract all. Okay, extract all. Okay, extract the Prime 95. Okay. Extract it here. Prime 95. Okay, no, not bad. 30 megabyte. Just stress testing. Okay, so let's blend all the above all the above. Okay, large stress memory controller and RAM. Okay, let's try it out. Okay, are you running it? Haven't run it. Oh, run already. Wow, memory 90% usage already. Okay, we're running this, but our computer still works well, right? Okay, 90% usage. If you look at the processors, I think Prime 95 now uses 6 gig of memory. Okay, the rest are still quite okay. So while Prime 95 using this much memory, let's see if we open Microsoft Word, things will hang or not. So things are running very slow now. I hope Zoom will not hang also like Zoom is also running in the background. You see some Prime 95. Okay, Microsoft Word. Hey, it doesn't use so much memory. Okay, now this is not too bad. Chrome is not too bad. Okay. Okay, so CPU is 100% now. CPU is being used 100%. Memory is being used much. I don't know. Okay, so the page pool here seems to be very small. So it seems that I'm not actually using a lot of this virtual memory. This one needs. Okay. So I think you can see basically this is what Prime 95 is doing. You can go and stress test your PC if you want to. Okay, let's stop the thing. Stop. Okay, stop everything. Okay, done already. So memory now drops. Okay. CPU performance now drop. Right. So I think our modern CPU these days not too bad. They seem to, especially Windows 10 especially. Okay, it seems to do a very good job of managing memory on that. Okay. So, but the thing is, if you ever run out of memory, say you're using only 8 gig, and you are doing some kind of photo editing or rendering stuff, right? Then you will need more memory than your operating system has. Okay. So what happens is that your operating system will do some kind of virtual memory. Okay. Basically, you will share memory. You will take some part of the secondary storage and copy the RAM inside. Okay. And right. So your application must time share lah, the memory. Okay, so maybe the apps in the background, they will copy the apps back into a portion in the secondary storage. Right? So this is called the virtual memory. And again, this is managed by operating system. It's transparent to programmer. As programmer, you don't have to worry about this. We'll talk more about virtual memory. I think when we talk about operating system. We asked, okay, in the earlier lecture, we said that registers provide temporary storage. Why you need cache? Right, because of this. Okay, go back here. Because of this, register costs super many dollars. Okay, super expensive. So you cannot afford to have kilobytes of registers. Your CPU will cost $20,000. Okay, so at most we only have 100 bytes of register only. Like I said, one register maybe one register 8 bytes. 64 architecture. You will only at most have maybe 10 registers. Okay, 10 or 12 registers in your CPU only. So you can only store 100 bytes. So 100 bytes is definitely not enough, right? Okay, if you think about it, one instruction is 8 bytes. So your register, you can only store what? 8 instructions. That's not very much as compared to your SRAM, right? And so you build this little cache here of SRAM, where maybe, so if you look at our SRAM, where's our system? Oh, did I close Task Manager? Am I open again? Task Manager. Okay. If you look at our CPU here, you can see we have L1 cache. Wow, 256 kilobytes. Not too bad, quite decent, right? 256,000 bytes. Right. Then you go at L2. L2 also quite decent, 1 megabyte. L3 is 8 megabyte. Okay, so it's not just one single cache actually, right? It's not just one single cache. Actually, here you have so outside here you might have an L3 cache. Inside here you have an L2. Then closer in the register they call it L1. Okay, so they go smaller and smaller and smaller and smaller. So this L3 is 8 megabyte. Okay, this is 1 megabyte. This is only 256 kilobytes. And again, this is our modern processor already. So this is how they do it, right? So registers, like I said, is only about 100 bytes. Okay, so if you look at this, this is already 256, not 1,000, 2,000 times more space than your register. Okay, so we can save money. But already, this L1 is very expensive. 1 gigabyte costs $400, which means 1 megabyte, okay, maybe it's about $4 lah, or maybe less lah, 40 cents, kind of a thing. Okay, 8 megabyte will cost a bit more. Okay. So that is the why we need to cache to perform the same job. In fact, if you look at all memory, they all perform the same job, right? All memory perform the job of storing data. Basically, they all do the same thing. SSD store data, RAM store data, cache store data, register store data. It's just a question of how fast they can read and write to this data. Okay? So, like I said, you cannot just operate a main memory because it's too slow. We cannot operate with just cache. Cache is SRAM. Because it's still too slow, not fast enough for the CPU. CPU operate at the same speed as register. But register is so insanely expensive. It is like I said, it's like the CPU itself built into the CPU, right? Into the core chip itself. Okay, so that's why it is quite expensive. Okay, L1 cache typically, maybe L1 cache typically is right next to the processor. Okay, it's built using SRAM, so it's slightly slower. Okay, but it's close enough to the processor. So what we want to have is this: we want to have a small amounts of memory that are very fast, but bring closer to the CPU. So this is the analogy of cache. Okay, why we have this cache thing? If you go and Google cache, cache is just this little storage thing. Okay, English word called storage sake. So here's a library analogy. Okay. Suppose you are studying in the library, right? And you want to go, and I mean, this is the olden days before you have internet or Google or what. So you study, you go or do your research, you go to the library, sit down there, go to the books, take a book. So imagine you want to take a book, right? Okay, so you go to the bookshelf, grab one book, okay, bring to your desk. But because of desk constraint, your desk cannot put too many books. You only can put one book on your desk. Okay. Or rather, maybe not the constraint. Maybe you're only reading one book. Right? You can read one book at a time. You're like the processor, read one book. After you're done reading the book, you're going to go back and put the book. Now, very troublesome, right? Every time I want to get new book to read, I must go back and forth, back and forth. So this back and forth is the delay. It's like the memory delay. Every time the CPU wants to get data from RAM, data from main storage, data from secondary storage, will take a long time, go there, grab a book, come back. Okay, so this is very troublesome. But what you didn't mind is that solution, right? You have a desk space. So suppose you make use of this desk space. I put the book here. So I go there, I grab books. I grab some books that I think I will need. Okay, grab a chunk of books, then I put it here. So if I really need a book, I don't have to go back to the bookshelf. I can just grab the book from my table. Okay, so this is the idea of cache. Okay, instead of grabbing line by line, instruction by instruction, data by data, small bit of data by data, I go and grab a big chunk. Okay, so you can see your registers only like 100 megabyte registers. Your L1 cache 256 kilobytes. Like I said, this is 2,000 times more. So you can grab a whole chunk, right, of data, one shot, grab the data into your cache. Then as your registers need, okay, you can deal with the data here. Okay. Okay, so basically what we do is we keep frequently and recently used data near the CPU in this little cache. Okay, then only when you cannot find the data you want. So happen there's a instruction that says, maybe the instruction jump somewhere else. Then okay, no choice. You have to go all the way to slower memory and fetch, right? So maybe you're doing your book reference, right? So you're doing research in your books. Your book, this article says refer to this other book, right? If we read journals and all this, there's always citations and references. So you refer. Suddenly you refer, the book is not on my table. Then no choice. Okay, you cannot go on with your research. You might get out of your seat, walk to the bookshelf, take the book, come back, right? But of course, when you take the book time, maybe you don't just take one, you take a whole chunk, right? Okay, just to save more time later on. Okay, so the thing about cache is a bit more predictive, okay, on how you grab the thing. Now, why cache works? How come it works? Like I said, when you go to the bookshop and grab a book, you don't just grab one book, right? You want to grab a bunch of books. But how do you know which bunch of books work and how come it works? Okay, the idea is that we have this principle of locality. Right. When you write your program, in a sense, your program is sequential, right? Now, even if the whole program cannot fit into the cache, okay, maybe only this chunk can fit into the cache. Okay. If I need an instruction from here, most likely this chunk of instructions all are related because the instructions follow one after the other. Okay, so I go and grab a big chunk of things. It's similar to library, right? Normally, library will sort all the related books together. So if you go there, assuming they do books on the same topic, everything they sort together, right, based on some system. So assuming they do, you go to library, you want this book, you grab 5 books to the left, 5 books to the right, you pull it all out. There's a high chance that what you need later on is among these 10 books, right? So similar idea here. Okay? Because your program access, usually the accesses your program need is quite local one. Okay, it's very near each other. Okay, just like you have for loop. For loop, the instruction keep repeating. So it's very near each other. Okay, so this is the idea behind cache. How come it can work? Okay, if you don't have this cache locality, then this cache will not work, right? Because imagine your library, the books are all randomly arranged. How do you know that these 10 books that you pull from the shelf is related? Then no use, right? You pull 10 books, none of them can be used later on. You can find yourself walking back and forth to the bookshelf. Okay, so that will be quite pointless. So the idea is that normally your data is one continuous chunk, right? Okay, like data or instruction. Okay, data is like when you access data, we know you access the function is one whole chunk of contiguous memory. Okay, so it's faster. Locality is where your program, so your program has a lot of instructions or data. If the data cannot fit into one cache, right? So you pull a block. If I need to pull another block, why is it that if I pull this block is useful? It's because all the instructions are close together. Right? If I need to use this instruction, the other instructions will be close together. So this is the principle of locality. Okay, in your program, your instructions follow one after the other. Right? So if I pull 100 instructions, right? If I need instruction I go to my memory, I pull I to I100. A high chance that the next instruction is all after I sequentially. Okay, so that's why the name of locality. If you don't have locality, then this thing will not work. If our instructions are all over the place, it will not work. So your compilers will try as much as possible to write instructions close together. Right? Okay, you try to group data okay, close together. So that's how this idea works. Okay? So locality, okay. There are two types of locality. Okay. One locality I mentioned before earlier on was a so-called spatial locality. Okay. If an item is referenced, nearby items will tend to be referenced soon. Okay, just like I said in a library analogy, right? You go to if the librarian sorts the books properly, okay, and it's related book, so I go to this book, I pull it out, right? The books on the right, okay, or left of this particular book, high chance is related to the same material, right? So very high chance that the book will reference each other. So if I pull these 10 books off the bookshelf, very high chance, okay, all I need is mostly in there, high chance. Right? Of course, not 100%, high chance. Okay, so this is called spatial locality. Okay. Now there's also temporal locality. Basically, if I find myself referring to a book very often, so I refer to this textbook, this book I'm looking through. I go to another book. I come back to the same book again. If I come back to this book again, there's a high chance maybe this book is a very core book, right? Foundational book. So I have to keep referring to it. Okay, this is called spatial locality. If an item is referenced, high chance that maybe you need to refer to it again. So this temporal locality in terms of time. Okay, maybe this book, you go look at something else, they ask you to come back with this book again. Okay, so this is a very important book. So of course, this book I will want to keep on my table. Okay, because I noticed that I keep accessing this book. I don't want to put it at the bookshelf. Okay, so this is called temporal locality. Okay, so these two types of locality. One is spatial. Basically, what is next to it tends to be related. Temporal means if I'm using it now, maybe high chance I will use it again. Okay, so in terms of cache, we exploit these two locality. Okay, so now some terminology of cache. Okay. We call a cache a hit if the data we want is found in a cache. Ding, we call a hit. The book we want is on our table. Okay, it's a hit. Okay, then in this ideal case, very fast. Data will come very quickly into my register. However, if what I want is not in the cache, then no choice. I must go to main memory and get it. Okay, so we have load the memory from, so it's called cache miss. It takes a long time for data to slowly travel all the way back to the processor. Now, when we are slowly traveling, it does make sense to keep a copy of Y in the cache, right? Why? Because temporal locality, right? I'm referring to Y. High chance I'm adding Y again. So maybe I just store Y here. Okay? Of course, this is simplified because there are different techniques, okay, to determine whether you're going to keep in cache or not. And these are the techniques we talk about in a while. Now, how do you map memory to cache? Okay, so this is the interesting thing. So memory, okay, so I go here. Okay, memory is one contiguous chunk of bytes, right? Contiguous. That's like a library bookshelf, right? A library bookshelf is, even though it's arranged in a shelf and blocks, right? You can serialize, right? You can number the books in the library as one contiguous book, right? From book 0 all the way to book 9099 or whatever, right? You can label them all contiguously like this. Okay? Now the thing is, when you want to grab a book, okay, you don't just grab a book. Okay, what you do is you typically grab by blocks. You don't just grab one book at one time, right? Because, like I said, no point getting one book, right? You want to exploit spatial locality. So you grab blocks at a time. Okay. So down here, okay, so what we down here I categorize is that normally we call words, okay, we call a 16-byte block a word. So normally we call 4 bytes to be one word. Okay. So 4 bytes to be one word. All right. Here we use a 4-word block. Okay. A 4-word block. 1, 2, 3, 4. So this is block 0. Okay. Again, this depends on architecture. So if you have 64-bit architecture, normally your word it might be 8 bytes for a word. Okay. So again, different architecture and design. Okay. No reason why we need to use a 4-word block. Right. So might be bigger lah, but we use 4-word here in our example. How if I say we use 64-word block, how to draw 64? Okay, so we're using small numbers just for our understanding. Okay, so this is what we call a block, right? So why is block size bigger than a word size? Okay, so word, okay, is typically basically what as an instruction. Okay, so you can think of it as one particular book instruction, right? By instruction. So we want to exploit locality, so we don't go and take instruction by instruction from the main memory, right? We take one whole block at one time. Like I said, we don't just take one book at a time. If one book is one instruction, then you find yourself running back and forth all the time, correct? Okay. Maybe book is not good analogy lah. Maybe a page of a book. Okay, if you take one page at a time, it's very silly, right? So normally you take a bunch of pages, right? And then it's called book, right? At one time. So that's why we arrange in blocks. Okay, so blocks can be multiple words. Here we use 4 just as an example. Typically, you can use 64, 256 kinds and stuff. So the bigger it is, the one fetch, okay, and is more effective. Okay, now there are 2 types of cache we'll talk about today. One is the fully associative cache. Okay, basically, fully associative means having total freedom. It means, okay, that any book you pull from the shelf can go to anywhere in your desk. Okay, so suppose let's say all the articles in the library are in books, right? So each page is one instruction. Okay, so one book is one block. Okay, one book is one block. So on my table, say I have 10 spaces for 10 books. Okay, so any book I take, I can put into any of these 10 spaces on my table. Okay, this is called fully associative. Any book I pull from the library, okay, I can put on my table. Okay, so now we talk about books. Books are like blocks. Okay, the individual pages are like your instructions and all that. Okay, so this is a fully associative cache. Okay, now the question is, imagine now the books have no book title. Okay, there are no book title. I mean, in memory, there's no title, right? So the books in the library have no title, but each book is numbered, right? From book 0 all the way to 9999, book 9999 book, okay? Book number. So I will read book 1, and then book 1, they say, oh, book 1 requires book 52. So I go to the library, find shelf 50, book 52, take book 52, of course, and all that. Okay. So the question is, if I look at my book, okay, but the interesting thing is, if I look at my book like this, okay, how do you identify which block is in the cache? Okay, so what we do is we need to have some cache ID. Okay, this is a bit complicated. Okay, let me see how to explain this. Okay, so suppose I have a slot 0, 1, 2, 3. Okay, on my table. Okay. I will need to put a tag. Okay, so this is more complicated because the title is not on your book. You think about it this way, right? You are pulling data, right? You're not pulling a book. So imagine a library. Okay, all the books in the library are there, but the title is not on the book, and the book is not numbered. It is a shelf slot that are numbered. Okay, you think about this. This is like your bookshelf, right? So there are slots in the. So every book the same size, there are slots you put in there. So it is the slots that are numbered. Right, slot a book shelf 0, 1, 2, the slots that are numbered. Okay, if I pull this particular book out and I take it out and put on my table, the book got no number one, so I must write the number. Like this is book number 521. Book number 521. Okay, I must write down 521 there. Okay, on my number. So I only a tag Basically, I must say, this book on my table here in this particular slot is book number 521. Right? So if I need to refer to book 521, I can refer to it there. Okay, so in this fully associative cache, every slot on my table, so these are all the slots on my table, I must maintain a special tag address. Of course, the size of this has to be able to fit all my entire memory space. If by now you have not realized, if my tag size is only 32 bits, how many books can I have? It's a little under 4 million. Yeah, 2 power 32. It's a little bit under, not 4 billion, a little bit under 4 billion, which is 4 gigabytes. Which is why if you are running Windows 32 bits, you can only have 4 gigabytes of RAM. Because you can only refer to 4 billion books. Okay, that's the limitation. So they will tell you, install Windows 10 64-bit. 64-bit, then now it opens up, right? You can access a crazily big number, and now 2 to 64. Okay, number of memory. Okay, so that's why with 32 bits, you can only refer to maximum 4 gigabytes of RAM. You put more RAM into your machine, PC or laptop, you get load Windows 32-bit. The Windows 32 will show you 4 gigabytes of RAM. You cannot access anymore because it doesn't have space to identify. Okay, basically the number tag of your bookshelf only have this finite number of digits, so to speak. Okay, so anything beyond 4 billion, there's no space to write anymore, so it ignores. Okay. Yes, so your cache tag must be the same as how much memory you have. Right, so if you're working with 32-bit system, then maximum you can only address up to 64 gigabyte, right? So you only have 64 billion books, so to speak. So if one book is 1 byte, then you only have 64 billion bytes in a sense. Okay. Of course here you right. Okay. Of course here you use block number. Okay. So it might be a little bit more efficient. Okay. So not say each block is not 1 byte lah. It's just a block. Okay. So your cache tag must be, the number of bits in your cache tag must be enough. Okay. To hold the block. So maybe if you say you have 4 billion books, but each 4 books is 1 tag, right? So you only need to store 1 billion tags, okay? So basically the cache tag is number of digits, number of bits needed to hold this amount. So the entire block number must be used to identify. Okay, so again, the issue is that this is resource intensive, right? Why in resource intensive is because, number one, you need to, when you want to check, okay, suppose you are looking for book number 512 inside there. Okay, and you have, say maybe you have 4 cache tags, right? When you want to check, we don't want to go one by one to examine which tag is the one that you want, right? We don't want to do that. We want to have a kind of a lookup. Okay, one shot. When I do a read here and read here, straight away you tell me, ding, this is 512, yes or no, kind of thing. Okay, so this kind of mechanism, this kind of circuitry is basically use comparators and takes a lot of space on the chip. So you need a lot of this circuitry to figure out, okay, basically to match lah. Okay, the kind of to match which in one step, in one cycle, to match which cache tag you want. Okay, so that's why fully associative cache is seldom used because of this thing, right? You need to examine all your, okay, basically your eye must open, look at all 10 books on your table and decide instantly which book you want. Right? Then your eye need to be very big. Okay, so you need to have a lot of, or maybe you need to have one assistant at every slot. Then you ask assistant which book you want, then he will say yes. Right? So it's very expensive to hire so many assistants. Okay, so we use direct map cache instead. Why direct map cache? The analogy is this. Okay, now suppose there are 26 locations in a desk. Each book can only go to one location. Now, if a book is in English, we say, okay, the first letter of the book is the title. So on my desk, I have A to Z, right? So if the book is Harry Potter, so I have H, it must go to the H slot only. Okay, so of course, if the books are all numbered, okay, with numbers, then we just use the modulo, right? Okay, so suppose we have 10 spaces on our desk, and all our books on the shelf are numbered. We just modulo 10, right? I just take the last digit. Okay, if the last digit is 0, you go to the 0 slot. If the last digit is 9, you go to the 9 slot. If I have 15 slots on my table, then I take modulo 15, right? I divide by 15 to get the remainder. So now every single book on my bookshelf goes to one particular slot. Now what is this? What's the advantage of this? I don't need to, my cache tag can be reduced, right? You don't need the full ID of the book. You only need to know, because the book is modulo. Say suppose I have 100 slots. 100 slots on my table. Okay? And I have 10,000 books, right? So book 0 to book 99999, right? If I have 100 slots, then I will be doing modulo 100, right? Which means the last 2 digits, right, will be the slot. So if on my table, I have slot 0 all the way to slot 99, right? Okay. So suppose I want to look for book number 512. I know that 512 must be in slot 12, right? On my table. Slot 12, correct? And to label this book, I don't need to put 512. I need to be set to 005. Basically, I need to store this digit in the cache tag. Okay, so now I only need 3 digits. Okay, in my cache tag, right? Only need 3 digits. As opposed to in a fully associated, I need all 5 digits. Okay, so my cache tag, I can print a smaller label. Right? I save space in my labels. Okay? Alright, so my cache tag only requires the most significant part, basically the leftmost part, okay, of the block. Of course, everything you put in binary, you just use position it is. Okay? Now, the thing about this map cache is that if I want to identify the book, I don't need to look at every single 100 slot at one time, right? I know that if I want to get, say I want to get book number, maybe I am 512, say refer to book number 627. Very simple, I go to 27 slot. Straight away I go there, I see, is the book in here, is the label 006? If it is, yes, cache hit, the book is found. If it's not, if this one is 127, oh, this book is number 12727, right? It's not what I want. Okay, so I will have to go to main memory and fetch the book. Okay, so this way, yes, it is not so flexible, okay, but it makes the mechanism, the retrieval, more simplified, not expensive. So you can, so your circuitry, remember this is all in hardware. In hardware, they must design wires and transistors and all inside there. So if you have very complicated wiring, everything, and wiring have to jump over everything, then you don't have enough real estate for other stuff. Okay, so here we sacrifice a bit of flexibility, have a little bit more simplified wiring, so we can have a bit more space to maybe make a cache a bit bigger. Okay, so these are all the trade-offs. Okay, so pros and cons, yeah, okay, so only possible, so any block can only go to one location. That is the key in direct map, directly map. Okay, so you use think of it as an analogy. The book that I put on the bookshelf can only go to one particular slot. That's the restriction. And because I have this restriction, okay, my circuitry can become much simpler. Okay, my lookup is much simpler. But of course, at the trade-off of not so much flexibility. Yeah. All right. So, what if you have cache conflict? Now you have conflict, right? Because different blocks can map to the same spot, right? Like, for example, book 612 and book 512 both will map into the slot for 12, right? And now you have conflict. How? Okay, so basically, you need to figure out, okay, whether to kick out 612 or keep 612, right? So again, there are certain algorithms at play here. Right? One, for example, is maybe you find that I use 512 more often than 612. So maybe I don't want to put 612 in. So I keep 512 in. If I need 612, then no choice, I go big main memory and take it. I don't go and install it. Okay? So there are different kind of schemes to figure out, okay, whether to replace or not. Okay? So in terms of access time, basically, this is what we'll cover in tutorial, right? Once you have a hit, okay, the time to access is just the time to access cache. right? So the processor says, I want to load a piece of data. It's not in my register. So I go to cache. Yes, X is a hit. Come back, copy the read back in the register. So this is the access time. Now, if you miss, okay, so I'll come here. I have some time wasted, okay? Oh, it's a miss. I must go to RAM, and I must slowly bring the data here and bring it back again. Okay, so this is called the miss penalty. So of course there's a rate lah. There's hit rate and miss rate. This is just math, basic math. Right? Hit rate is basically if I want to access 10 memory location, out of 10 memory locations, six of them are in the cache. My hit rate is 6 out of 10, right? Miss rate is just 4 out of 10. That's simple math here. Okay, so this is just so on average, right? What's the average access time? So the hit rate multiplied by the hit time lah. Right? Say if 80% of the time I get a cache hit, okay, and my hit time is say 0.1 microseconds, maybe example lah. Okay, so this is 80%. The other 20% of the time, my penalty is 100 microseconds. Example. Okay, so you have penalty. So what's the average? The average just multiply out and add, right? This is a simple average formula, right? Simple average formula. Okay, so some examples here. Okay, I won't go through this example. It's just a simple formula. Okay, so here we talk about this block replacement algorithm. Okay, so there is this thing about alternative mapping scheme, right? So we won't talk too much about it. Basically, you can imagine that, right? Fully associative got advantages, right? Meaning very flexible. Any block we want can go anywhere. But the lookup mechanism is complex. Direct map, more restrictive, but the lookup mechanism is cheaper. So it is possible to design some cache to be a hybrid between fully associative and direct map. Okay, you can design it some way, right? So you can have a certain trade-off, okay, between the two, right? So we talk about block replacement algorithm. So block replacement algorithm, I'll just mention here. There are two general replacement algorithm. Okay, first one is the least recently used. So if you want to replace the block, okay, you replace the block which was least recently used. This is of course assuming fully associative lah. Okay. If you're direct map, then no choice lah. Direct map most of the time you bring in, you just replace already. You can't do anything about it. Okay. If you're fully associative, you get to choose, right? You bring a new book from the bookshelf, you can choose which of your 10 slots you want to replace. So one scheme is replace the oldest lah. Right? Which slot was the the earliest that you never use. So that one, I would think based on temporal locality is maybe very stale already. Okay, the book has been lying there for eons, nobody accessed it. So it's quite stale. If I bring a fresh book, I'll replace that book. Okay? That is called least recently used. Okay? Or another replacement would be the least recently used. I can't think of any other replacement now. The other one would be the last used. One is the very stale one, okay, which is the oldest one. The other one would be the least that was basically the last access one, or they count the frequency of access. How many times you have accessed the cache? Okay, how many times you have accessed it? Okay, so this I mean there are many other replacement algorithms, okay, that you can try, okay, or people can talk off and figure. The whole point is that, I mean, without benchmark and without knowing what kind of data it is, okay, it is not easy to figure out which is the best algorithm. Okay, okay, multi-level cache. We see that in processor with a different level of cache. Okay. This one, the i7 has 32 kilobytes of L1 instruction cache, L1 data cache, 512 kilobyte of L2 cache, and then all the way up, okay, 2.5 megabyte of LCC. So if you look at your CPU, this is the CPU. Okay, so we use a CPU. You see this is like the 6 core of the CPU. Here you have L3 cache. L3 cache is shared between all the CPUs. So your L1, L2 cache sits inside each core. Well, each core got its own cache kind of thing. Okay, and memory controller and all that. This one is a smaller cache because you have many core. Okay, this PC I'm using maybe have fewer cores. Okay, this one can have bigger cache. Okay, and we did simplify all this cache address calculation. Right, the calculation I showed you before, we did heavily simplify them. Okay, so this is the whole idea of cache. The whole idea is we want to bring chunks of data at one shot. Okay, rather than go back and forth many times, we want to bring a whole chunk of data, a block of data out from memory, okay, and put it somewhere near the CPU so we can exploit it. Okay, the locality of it. So next time we want another book, another block, okay, it is already in our cache. It's very near. Okay, not so much of wanting another block. Okay, we want to access the pages in the block. Okay, in the sense, right, the different instructions in one block. Okay, so we take advantage that in a book, all the pages are most likely related, right, to each other. So a block of memory that we pull from the chunk of memory, pull the instructions in there usually are sequential, right? Your instructions is one after the other. Okay? So they are all probably within the same block. Okay, so that's what we are exploiting in cache. Okay, any questions?